Okay, so good morning, everyone. And this is the last online Ithaca meeting for this year, 2022. And before we start, I would like to recall you that we are going to have a physical Ithaca meeting in December and late December, I think 21 and 22nd of December. And you can check it out on our webpage, and we would be happy for anyone to be there. This is going to be in Pisa for this year. So if you want to visit Pisa, this is our occasion. And today we are going to have Nicola Di Vittorio and George Rotis. And the first speaker of the day is going to be Nicola with a gentle introduction to derivators. Nicola, take the stage whenever you want.
Okay, thank you, Ivan, and thanks to the organizers of the Ithaca Fest for inviting me to give a talk and for having this morning session, which is an evening session for me in Australia, that allows me to talk, in reasonable times, because I have very many time zones apart from Italy. So today, I'm going to give an account of the theory of two derivators, which I've been developing for my PhD project under the supervision of Dominic Verity. Basically, this is an attempt to give a higher dimensional version of the theory of derivators. So in some sense, the theory of derivators can be seen as a way to axiomatize homotopy theory, or in other words, as an approximation to infinity categories. So a derivator can be seen as an approximation to suitably complete infinity category. And in the same way, two derivators should be thought as a way to axiomatize infinity category theory, or in other words, as an approximation to some suitably complete or co-complete infinity two category. But so let me start. So this talk is divided in 4 parts. The first 3 are basically some recollection of some preliminaries that I need in order to be able to talk about two derivators. So first of all, I'd like to talk a little bit about derivators in a classical context, and which are one of the one of the inspirations, well, one of the main inspirations for this theory. And then I want to talk about infinity cosmoi, which are like a model for this theory in some sense. So like infinity cosmoi can be thought as one example, or at least the theory of infinity cosmoi as developed by Real Verity can be thought as an instance of the theory of two derivators. And the last thing I want to talk before going to the theory of two derivators is this bit technical construction, the enriched, so the collage construction for enriched profunctors. It is a bit technical, but is needed in order to give one of the axioms for two derivators that's gonna need this kind of construction. And at the end, I will talk about two derivators. So one of the goals of derivator theory was to provide some formal way to compute homotopy limits and co-limits that doesn't really depend on some chosen model of infinity one category. So in other words, if we have a category of diagrams of shape T inside a homotopical category M, classically we can define the homotopy limits and co-limits as derived functors of limits and co-limit functors. But as we see in the domain of this of the homotopy limits and homotopy co-limits functors, we have to take the homotopy category, or well, at least the localization for homotopical categories, which will be the homotopy category if the homotopical category is also a model category, this is going to be the homotopy category of it. So of the functor category, but this is in general different from the category of functors inside the homotopy category of M. So usually one says that this is a category of coherent diagrams, and while the category of functors inside the homotopy category is the category of incoherent diagrams, because in some sense the category of functors of the category of diagrams of shape T inside the homotopy category of M encodes diagrams that are just commutative up to homotopy, but that homotopy is no longer coherent. But these two categories are related in some way because of the universal property of the localization. But this functor that relates the category of coherent diagrams and the category of incoherent diagrams is not an equivalence in general, just because because homotopy limits and homotopy colimits are not limits and colimits in the homotopy category. But we can ask what properties does this functor have, and this is like one of the starting points of the theory of derivators. So before we can talk about derivators, we have to define the notion of a pre-derivator, and then a derivator is just a pre-derivator satisfying a list of axioms. So the idea is to generalize this construction that we see that are seen for homotopical categories or model categories to a more general framework when we are interested in computing homotopy limits and colimits of some diagram shapes, and we collect these diagram shapes inside a sub two category of the category of the two category of categories that is closed under some constructions. Usually we ask for this two category to be, well, usually we ask that if a category is in dia, then the slices of this category for every object of the category is also in dia, and other closure properties, like for the taking the products or taking the pullbacks, and so on and so forth. I mean, for the sake of simplicity, one can also think about dia to be the full, like the whole two categories or small categories. Then a pre-derivator is just a two functor out of this two category inside the categories or not necessarily small categories. And for some notation, we usually use the upper star notation to denote the image of a functor of an auto transformation under D, and then D of one. So one is the terminal category, is called base of the fiber over one. D of Y is the category of coherent diagrams, and D1 of Y is the category of incoherent diagrams. And this terminology recovers the terminology we have seen for homotopical categories, or in particular for model categories. In fact, one of the examples of a pre-derivator is the one associated to a model category, if the category is nice enough. And others are the representable functors are another example of a pre-derivator. And also we have a notion of we can shift a pre-derivator using a category I, just taking the product. And then this is interesting because basically we can just work on the base of the derivator by shifting. As we saw before, for homotopical categories and model categories, we have a functor between coherent and incoherent diagrams, but we actually have this same. So in general, if we have a pre-derivator, we have a way to construct a comparison functor between the two, and this is basically constructed as follows. So basically, if we have an uncoherent diagrams. If we have a coherent diagrams, we can send it to the functor that takes an object of I, and it sees it as a functor from the terminal object, from the terminal category to I, and then applying D gives us a functor that can be then applied to X. In other words, this functor is the image of the functor that comes from the action of the prederivators on home categories through the isomorphism that are the ones coming from the fact that categories, well, for categories we have the adjunction between the product and product and ohms, internal ohms. Last thing we need in order to speak about derivators are Beck-Chevallet squares. So this is something which is useful to encode the notion of pointwise scan extensions, because basically one of the axioms of derivators is going to be it's going to need this construction. So if we have a square, we can with the top and the bottom morphism having a left adjoint, we can pass the with the unit of the first adjunction and the co-unit of the second adjunction, and we get another square. And so the first square is called left Beck-Chevallet if this new square is filled by an isomorphism. Why is this interesting? Because we can express the ordinary formula for pointwise scan extensions, the one that that can compute scan extension as limits and colimits, by asking that this square is Beck-Chevallet, left Beck-Chevallet for left scan extension, and there is a notion of a right Beck-Chevallet for right scan extensions. So therefore, a prederivator is just a derivator. It's called a derivator if it satisfies these axioms. So the first one, it just asks for the coproduct of two categories, I and J, to be sent to the product of their images. For the second, and this is this can be generalized in a straightforward way to the two-dimensional version. And the second axiom asks for the conservativity of this underlying diagram functor that relates coherent diagrams and incoherent diagrams. Or in other words, if we think about the representable prederivators, this is just saying that every natural transformation which is level-wise an isomorphism is a natural isomorphism, and this is also generalizes in a very straightforward way to derivators. While for the third and the fourth axiom, we have to be more careful. So in this case, in ordinary derivator theory, the third axiom asks for left and right adjoints to the precomposition functor for every functor in dia. And these left and right adjoints are called homotopy scan extensions in a way that is analogous to how scan extensions are defined in category theory. And furthermore, these homotopy scan extensions are pointwise. So these squares are sent by the two Beck-Chevallet squares. Usually one also asks for other axioms. For instance, for strong derivators, one asks that some particular underlying diagram functor, so the one associated to to the walking arrow are full and essentially subjective for every category in DIA. All right, and then as an examples of derivators, we basically have the previous examples with whenever we have some extra conditions, for instance, on a category, like to be complete and complete, the associated, so the onto functor associated to it is a derivator because of basically because this is just how things work in category theory. So we can compute we know that can extension exists and can be computed whenever C is complete or complete. And then if we have a derivator and we have a category, the shifted pre-derivator is also a derivator, and then the assignment that takes a category and gives the homotopy category of the functor category for a model category M defines a strong derivator. As an application of the theory of derivators, we see that homotopy can extension in this context recover the notion of homotopy limits and colimits that we define as derived functors of the limits and colimit functors. So then I'd like to talk a little bit about infinity cosmoi. So we know that if we have a simplicial set, this simplicial set is called a quasi-category if every inner horn can be extended. So so we have a diagram of this form, and quasi-categories form like they assemble into a category, which is a subcategory of the category simplicial set. So this also furthermore is a full subcategory. So we consider the morphism simplicial set are the morphism or quasi-categories are just a morphism of simplicial set, and also this is a Cartesian closed category, and also the so quasi-category are fibrant objects of this model structure that one can put on simplicial sets. That's called the Joyal model structure. Last thing we need before we can talk about infinity cosmoi is the notion of isofibration. So if we have a morphism of quasi-categories, this is called an isofibration if is an inner fibration. So for every inner horn, so we have that the first square admits a lift for every inner horn, and also as this lifting of isomorphism in the sense that we have a lift also for the second square. Quasi-categories with isofibrations that we defined form an infinity cosmos. In general, an infinity cosmos is a category which is enriched over quasi-categories and is equipped with a class of maps called isofibrations that satisfy two axioms. One axiom is on K, so K has to be complete in an enriched sense, and then the other axiom is on this class of maps. So this class of maps have to be closed under some constructions. And so as I said, quasi-categories are with the isofibration that we defined before are an examples of an infinity cosmos. But furthermore, the category of Kan complexes with Kan fibrations, isofibrations is another example. But also the category of categories with the isofibrations on categories and other models of infinity one categories, and also sliced versions. So for every infinity cosmos, I can consider the infinity cosmos of isofibrations to an object of the infinity cosmos, and so on. One key observation that Real and Verity use a lot inside their theory is that many constructions, a lot of the theory of infinity cosmoi can be developed inside some quotient of them, which is called the homotopy2 category. So in general, an homotopy2 category is so if we have a quasi-category, we can consider it's a homotopy category, but this is a functorial process, and furthermore, this functor preserves products. So it induces a change of base to functor from quasi-categorical enriched categories to cat-enriched categories, or in other words, two categories. So the homotopy2 category of a quasi-categorical enriched category is just the image of it under this two functor. So for instance, one example of a quasi-categorical enriched category is an infinity cosmos, but this is a more general notion. So the enriched collage construction is a tool we use for generalizing the notion of Beck-Chevalier squares to this enriched version, this enriched context, and then it's a bit technical. So basically, if we have two enriched categories A and B, we can consider an enriched profunctor between them, which is going to be just an enriched functor from the tensor, from the monoidal product of B op and A. So this is just the category, the enriched category that has as objects the products of the objects of B and the objects of A. So we have pair of objects. The first is from B, the second is from A. And the ohms are just taken, like, since we know that both categories are enriched over V, we just take the tensor of V, applied. So like we have the first components of this V category. We take the tensor with the second components. Okay, so the collage of this V profunctor is then a V category, which has as objects the coproduct. So we have two copies, one where we have a copy of A and a copy of B, and then we can see that so the collage, the object, the ohm objects. If we have two objects of the collage, the ohm between the first and the second is the ohm object of A if they're both in A, and is the ohm object of B if they're both in B. If the first is in B and the second is in A, we just take the action of the profunctor, and we take the initial. Well, we took V to be nice enough base of enrichment, so like complete, co-complete, and monoidal close. So we can talk about the initial object, and so this is going to be the last case. So if Y is in B and X is in A. As a piece of notation, if we have a cospan in VCAT, we can consider that this profunctor, which is kind of a representable profunctor in some sense, and we usually denote the collage of this as like the collage of these two functors, but it's more technically correct just to see this as this profunctor. Why is this interesting? Because basically, well, when we work with enriched categories, it's no longer true that every limit. So the the interesting notion of limit and colimits are weighted limits and colimits, and so we can see can extensions are some kind of weighted limits and colimits, but they are not longer, they cannot be expressed in general as conical limits and colimits like for categories. So in order to talk about pointwise formulas for can extensions, a way that I mean, one can realize this notion is by using this result, which holds for some nice basis of enrichment. So basically, if we have a functor and a weight, we can express the weighted limit as the can extensions along of the functor f along the inclusion of a inside the collage of w, when we see w as a profunctor from A to the unit V category, so the category with so the enriched category with one object and the given by the unit of V. So and there is a similar formula for computing weighted colimits by using limits. By using left can extensions, and then yeah, the point there is the point of the unit V category, because we know that in the collage we have a copy of A and a copy of the unit, so just a point. So that's going to be that. So the idea was to define pointwise can extensions of the functor the enriched functor f along the enriched functor k as this right and left in case of the left can extension. So it was the right extension in this case of the functor along this inclusion. All right. Last thing I need to say is that if we want to go from derivator to derivators, one can think that it's enough to substitute to the category of so the two category of categories, the three category of the three category of two categories, but this is not really that interesting because it's too strict. So we need to enrich over the pseudo greater tensor product instead. If we have two categories, well, the pseudo greater tensor product between those two categories in general is a bit complicated. But if we restrict us, just to give an idea, if we restrict to the working arrows, the product of the working arrow with itself is just strictly commutative square, while the pseudo greater tensor product of the working arrow with itself is a square which commutes up to isomorphism. The interesting feature of this tensor product is that it is monoidal closed, and the internal ohms are the two categories of two functors and pseudo-Nato transformations and modifications. And why we want to have pseudo-Nato transformation and not two Nato transformations? Well, because one of the axioms for derivators was kind of asking us to be able to detect equivalency, well, isomorphism level-wise. So when we go one level up, instead of having isomorphism, we have equivalencies, and it's not longer true that two Nato transformation, which is an equivalence level-wise or component-wise, is an equivalence in these two category. But for pseudo-Nato transformations, this is true. So a strict two Nato transformation is not true, in general. I mean, this property is not true for two-dimensional transformations, but it's true for two-dimensional transformations. So that's why we want to work with this tensor product instead of the just the Cartesian product. So then the notion of a pre-derivator generalized to the notion of two pre-derivator, which is some sort of a tree functor, which is called a normal triomomorphism. So basically, when we consider a normal triomorphism between some sub three category of the three category of two categories, the gray category of two categories, to the category gray, which is the two cut with the pseudo gray tensor product. In unpacking the definition, we have a function. So two pre-derivatives consist of a function from objects of dia to objects of gray. So a function, so an assignment for every small category, we get for every small two category, we get a two category, which is not necessarily small. And then we have at the level of ohms, we have strict two functors, and but compositions and identity one cells are not preserved strictly anymore, but they are preserved up to a pseudo-Norton equivalence. And also the associativity of one cells is just up to equivalence, and this equivalence assemble inside the so they have to satisfy some other coherences. Well, they have been like the ones that I've showed on the right. Well, they have to be so this square, this diagram must commute up to isomorphism, and this isomorphism also satisfy other coherences. So examples for two pre-derivators are ohms as usual, and then we have the notion of a shifted two pre-derivator of a two pre-derivator, and but probably the most important example is the two pre-derivator associated to a model category, which is enriched over simplicial sets with the Joyal model structure. So basically, we can take a two category and think about we can think about the two category as a simplicial category just by taking the nerves of the ohms, and we take the category of functors, well, the simplicial category of functors from J to M, with M is enriched over a simplicial set with the Joyal model structure. This is still enriched over the Joyal model structure. So we take the homotopy category and we consider cofibrant and fibrant object inside of that. And for the action on one cells and higher cells, we need to cofibrantly replace, because the precomposition functor, which is in the image of this, because the precomposition functor doesn't preserve cofibrant objects if we consider projective model structure on it. We could have defined this in terms of the injective model structure instead, but basically for a number of reasons. Well, I mean, we know that the projective and injective model structure in this case are equivalent. So the conjecture, I didn't show this yet, but I suppose that there is a tri-equivalence between this pre-derivator and the one defined using the injective model structure and the fibrant replacement instead. But yeah, I mean, this is enough to be able to talk about pre-derivators associated to simplicial, so to categories enriched over a simplicial set with the Joyal model structure. So two derivators are then two pre-derivators that satisfy extra properties. The first one, as I said before, is just basically the analogous to the one that is enjoyed by ordinary derivators, so sending coproducts of two categories to products. And this is satisfied by our examples, our main examples, so homes and two prederivators associated to a model category enriched over Joyal, and then also is stable under taking under shifting. The next axiom is an enhancement of the axiom on underlying diagrams, and this is the way in which one can find this this underlying diagram. Two-functor is basically the same as we saw before, just going back and forward through this adjunction. But now in this case, the internal ROM is, I mean, the adjunction is no longer like given by the Cartesian closeness, but the fact that the great tensor product is left adjoined to the taking the like homes, but with the pseudo transformations with as one cells. And this this two-functor is one asks for this two-functor to be conservative on one cells, and basically this is useful to detect level-wise equivalences. Furthermore, there are other conditions that one can give to this diagram two-functor, like these two. So we can talk about the free-living adjunction, and can internalize basically adjunction in using this functor, this two-functor, and we can internalize slices. So we have some diagram shapes that give us two-functors, diagram two-functors that are smothering. The last two axioms need to be modified a little bit, because since we are enriching over the pseudo greater tensor product, we cannot longer talk about. I mean, we have to make our notion of adjunction weaker. So instead of having adjunctions, we have bi-adjunctions. So bi-adjunction is basically are formally analogous to adjunctions, but the triangular identities are now filled by isomorphism. By isomorphism, I mean invertible modifications. So the last, this equivalent axiom, so the axiom that is the equivalent to the one that we have in for derivators talking about adjunction to the precomposition functor, give us bi-adjunctions to the precomposition functor. So basically, we ask that every two-functor in dia induces a bi-adjoint triple like this. And our examples satisfy this this axiom. So the pre-derivators associated to model categories enriched over Joyal satisfy this axiom, and this axiom is stable under taking shifts, and it's also satisfied by representable two prederivators, so the one that are homes, basically. Whenever D is complete and incomplete. Okay, so the last axiom that I will talk about today is the one that corresponds to pointwise scan extensions. So before we were able to talk about pointwise scan extension using Beck-Chevalier squares. So in this context, we introduced these diagrams that involve collages of profunctors. So the first couple of diagrams are sent to some other diagrams that are filled by equivalences, because compositions are preserved just only up to equivalence. But we also know that precomposition functors have left and right biadjoint, so we can paste with units and co-units and we can obtain these two morphisms between that we see below. And basically we ask for this to be pseudo-natural equivalences. This is like formally analogous to the thing we said before, by that we defined pointwise Khan extensions by means of Khan extensions along the inclusion of an enriched category inside the collage of these profunctors. So for the last axiom is just asking us to I mean, we want that every functor, every two functor in dia, and every object in B. So if the functor goes from A to B and B is an objective of B, we want that these diagrams are exact. In other words, that Khan extensions are pointwise. And the examples are the same as before. So these examples we have, they also satisfy this new axiom. And as a nice application of this, we know that we know from category theory, we know that Khan extensions along fully faithful functors are actual extensions, and we can enhance this result inside the world of two derivators. So if we have a fully faithful two functor, which is meaning for this we mean that there is an isomorphism at the level of home categories, then the unit of the biadjunction is a pseudo-natural equivalence. So this Khan extensions are in some sense are actual extensions. Okay, so this is it for today. Thanks for your attention.
Thank you very much, Nicola. And we have a round of silent applause as always. Thank you for talk. And now we open time for questions. So if someone has questions, they can unmute themselves and ask a question.
Maybe I have a question.
Yeah.
In the case where B in your last red frame is the terminal category, so you're considering something like a homotopy, two limits and two colimits.
Yeah, basically, yeah. This is just it's going to be that.
And do you think this will agree with the notions of homotopy of, let's say, two limits and colimits for infinity two categories that are in the literature already?
I'm not sure about that. I guess I should have a look to that.
All right, thanks.
Thank you.
I also have a question for you, Nicola. Can you tell us a little bit more about your motivations? Like, what is exactly that you envision with this theory? What?
I mean, it was kind of a way to axiom. Well, there are many instances of this can be found already in the theory of infinity cosmoi. So I guess one goal was to think as infinity cosmoi like secretly as a two derivators. So to see what, just like I guess we can associate a derivator to an infinity category, we can associate a two derivator to an infinity cosmos, because that's just an example of a category enriched over simplicial set with the Joy-Armstrong structure. So yeah, so basically I don't know, was just a way to axiomatize the practice of like infinity cosmology, like that should be thought more like like a model for this theory of two derivators. Yeah, so it was, yeah, it was just the purpose of just an attempt to find a theory that can be useful for that, but also to capture other examples like of infinity two categories, I guess.
Okay, thank you.
Thank you.
So do we have other questions for the speaker?
There is a request on the chat.
Oh, thank
Yeah,
you.
some
Someone asks for
references.
okay. Please.
Yeah. I mean, I should put this on archive at some point. I've wrote a thesis on the. I mean, do two pre-derivatives for my infinity cosmos. This is interesting. So George asked if two pre-derivators form an infinity cosmos, or maybe a two cosmos. This is very interesting. I should think about this. Thanks. So yeah, I'm not sure, but it's something which definitely look at.
But if I can
as
comment
for
on this, to show something like this, you would need some Joyal simplification enrichment on two derivators, right?
Yeah.
Right.
So maybe for as a reference, well, maybe I stop sharing. I can send my thesis. At some point, I'll put this on archive as well.
Sorry, I got distracted, downloaded the file. I should be back to sharing. Okay, so if there are no more questions for the speaker, we should thank him one more time. So thank you again, Nicola, for coming today. And
thank you.
Silent applause, at least you can see people clapping, which is something. And now we should wait 5 minutes for the next speaker.